Homework 3 hints. On the first problem, we're looking at the test for divisibility by 11. It says 11 is a divisor of n if and only if this alternating sum of the digits is divisible by 11. And this just boils down to knowing one thing. What does a decimal representation of a number mean? That just means that n is ak times 10 to the k plus ak minus 1 times 10 to the k minus 1 plus a1 times 10 plus a0. And now just look at this equation, mod 11. And it should just pop right out. Number 2 is a test for divisibility by 7. So again, we start off with a decimal representation of a number, k plus 1 digit number, and the claim is that n is divisible by 7 if and only if we drop the ones digit, subtract 2 times the ones digit from the remaining number, the truncated number, then that number needs to be divisible by 7. So it gives us an iterative way of making a smaller number that we test for divisibility by 7. So I think the key idea here is note that n can be expressed as 10 times m plus a sub naught, where m is what? Well, m is just the decimal number whose digits are like this. So if you take 10 times that, that shoves a 0 into this place, and then you add the ones digit, and you get n coming out. Okay, so with that in mind, now view this as a congruence problem. So 7 divides n is equivalent to saying then that 10m plus a0 is congruent to 0 mod 7. And we want to show that this is equivalent to showing that this number right here, and what's that number? Well, you want that number to be divisible by 7. So ak a1 minus 2a0. 7 will divide that is equivalent to saying, well, what is this? This is the number m. So m, 7 divides m minus 2a0. Turn that into a congruence and show some connection between these two. Okay, and then you can just test these numbers by repeated application. Problem 3. So you've probably noticed when you do decimal expansions of 1 over primes, you get these interesting repeating patterns, like 1/7 is 0.142857, and that just keeps repeating. And notice the length is 6. And that value of 6 is related to the fact that this is a number 7. And so in part C, we're eventually going to try to characterize those primes for which the repeating cycle is 1 less than the value of the prime, like 1/7. So what is the connection then between the length of the cycle and the order of 10? So in this problem, you can make the assumption that 1 over p does have a repeating decimal. So you don't need to prove that fact. So we get to assume that 1 over p has a repeating decimal. Now, a priori, there could be some initial digits, and then the repeating cycle begins like this, like that. And k is the minimal length of the repeating cycle. So we'll just put a bar over the digits a1 through ak. Now, it'll turn out that L is really 0. There isn't any initial stuff. But in your initial setup, we only know that it's a rational number. It'll have some repeating decimal at some point. And now multiply by various powers of 10. So if I multiply by 10 to the k plus L, I get this decimal number point, the repeating cycle. And if you multiply by just 10 to the L, you get the B part, point, the repeating cycle. So this is a trick that you learned long back for how do you turn a repeating decimal into a rational number. You get two different values that have the same repeating part here, and then when we subtract, we discover that 10 to the k plus L minus 10 to the L times 1 over p is an integer. And now just turn this into a congruence. So this will say something is congruent to 0 mod p, and you're going to discover the connection between the length of the cycle and the order of the element 10. And then deducing k divides p minus 1, that's just one of our theorems on the orders of elements in groups of units. And then likewise, when k is the full length, so the order of 10 is the order of the group of units, what do we call those type of elements? There's a name we give to those type of elements. And incidentally, it's conjectured that you get this full length roughly 37% of the time. So 0.3739, this infinite product here, is the fraction of primes for which 1 over p has a cycle of length p minus 1. Number 4. This is just a Chinese remainder theorem problem. Let me go ahead and just do a similar example. Because there is a strategy to try to minimize the amount of computation. So generally you want to start with the largest modulus right here. And so I'd say x is 2 plus 37t, and then work your way down. So plug that into the first congruence, and we get 2 plus 37t is 5 mod 13. Reduce 37 mod 13, and it's negative 2. Bring the 2 over to the right side, so I would get negative 2t is 3. And then find a multiplicative inverse of 2. Well, let's just multiply by 6 on both sides. So negative 12 is plus 1. So we get t is 18, which is 5 mod 13. And thus, x is 2 plus 37 times 5 mod 37 times 13. And then we take this value and plug it into equation 3, which has the very smallest modulus. So equation 3 now tells us, putting in x to be of this form, so it's 2 plus 37 times 5 plus some multiple of 37 times 13, say s times 37 times 13 should be congruent to 1 mod 5. and very quickly collapse this down. So this term is going to go away because it has a 5 in it, and this is 2 times 3. So you get 2 plus 6s is 1 mod 5. 6 is 1, so s is -1, which is 4 mod 5. And then you plug that back into the equation for x. So x is congruent to 2 plus 37 times 5 plus s, which is 4, times 37 times 13 mod the product. And then you can, you could have multiplied these things out as you went along, but now it's just a matter of multiplying that out. Number 5. Find a primitive root mod 7 to the 500 power. So step 1, you've got to get a primitive root mod 7. And you just start with trial and error. So you test 2. So you want to, which means find the order mod 7 of 2, and then you test 3 if that fails, and then test 5 if that fails, etc. Okay, so once you find a primitive root mod 7, let's say A is primitive root mod 7, you look at the Fermat little relationship. So you calculate this, a to the p minus 1, which in this case is a to the 6th power. No, we just calculate this as a number. You calculate a to the 6th, and you want to say that it's equal to 1 plus k times the value 7. And if 7 is not a divisor of k, then A is a primitive root mod any power of 7. Now if 7 does come out to be a divisor of k, you can do two things. You can either go back and find another primitive root in your list, or more simply, you can simply add 7 to A. So if this fails, just use A plus 7 as your primitive root. Find an element of order 10 in G125. Find an element of order 10 in G125. Okay, so let's find the group order. This is 5 cubed. So phi of 5 cubed is 5 cubed minus 5 squared, which is 100. And this is a cyclic group. Okay, so let's find a generator. And you do that like in part A. So let's say A is the primitive root you've just found. So again, just test 2, 3, and find one that's a primitive root. That works out. And now if I want to find an element of order 10, so A is an element of order 100 then. It's a generator for that group. And now use the theorem that says the order of A to any power n is the order of A divided by what? There's a theorem. And then you're just going to want to get this set equal to 10, and then you can solve for n. Okay, so I'll let you look up the theorem on what's the order of a to a power. Problem 6. Find the order of 7 in the group of units mod 2 to the n. And I've given an outline of how to go about doing this. So first of all, explain why the order must be some power of 2. And, well, just think about what is the cardinality. And if you have an element in any finite group, what's the relationship between the order of the element and the order of the group? Next, prove by induction that 7 to the 2 to the k power has this form. So you've got a base case, test that out when k is 1. And then in the inductive step, all we do is square this equation and show that it has the desired form. So base case, and you've got the inductive step. And I think it's pretty straightforward. So just square both sides. Conclude that the order is 2 to the n minus 3. So after having done part 2, you're going to discover that 7 to the 2 to the n minus 3 power, so that would be obtained by setting k equal to n minus 3, is congruent to what? Mod 2 to the n. So set k equal to n minus 3. And what if you took a slightly smaller power and you looked at 7 to 2 to the n minus 4 power? What's that congruent to? So we're trying to show that this right here is the smallest power that would give us 1. So I want to prove that if we had one smaller power, it's not going to equal 1. And again, I use part 2 for both of these, just with a different value of k. Problem 7. So what's the trick here? So the Euler phi function is multiplicative, but that means we have to start with two relatively prime numbers. So if they're not relatively prime, this is the fudge factor right here. And it's very easy to see that this is a number bigger than 1, and so you get part B very quickly. So I think to get part A, it's convenient to use the following form for the Euler phi function. Phi of m is m times the product p divides m 1 minus 1 over p. Now this product means a product over the distinct prime divisors of m. So use that notation, and so this would be mn times the product over the distinct prime factors of m times n, and then phi of n, you'll have a similar thing, and just compare these things, and it should come right out. Problem 8. Prove that there are arbitrarily large gaps between consecutive square-free numbers. So we've got a number n, which is a square-free number, let's say. And then you'll have n plus 1, n plus 2, and I'm going to create a great big gap, n plus k, and then n plus k plus 1, and this will be my next square free number. So what we're looking for here is that these k consecutive numbers right here, from n plus 1 to n plus k, should not be square free. So I want one of them to be divisible by a square, n plus 2 should be divisible by some other square, and so on. So let's have a, say, 2 squared to divide n plus 1, and maybe 3 squared to divide n plus 2. Okay, let's see. What number do you want to divide n plus 3? So I'm going to be turning this into a Chinese remainder theorem problem. So you want to pick these factors so that they are pairwise relatively prime, and then view it as a congruence problem. So this would mean that n plus 1 should be congruent to 0 mod 2 squared. And the second one should be n plus 2 is congruent to 0 mod 3 squared. And keep going like that. And then apply CRT. I think I've given you enough of a hint on that one. Number 9. Prove that for any prime other than 2 or 5, there's infinitely many numbers in the sequence 1, 1, 1, 1, 1, 1, 1, 1, 1, divisible by p. So make this a congruence problem, and let's just rewrite one of these numbers. So when you're talking about 1, 1, 1, 1, that means, let's do it like this. Say we have k digits here. Let's say k minus 1 digits. So that's the ones place. This is the tens place. And this would be the 10 to the k's place right here. So what is that? 10 to the k, 10 to the k minus 1, plus 1, which equals what? Use the geometric series formula. And then we just want to set this to be divisible by p, so set it congruent to 0 mod p. And then think about, what do you know about orders of elements, and et cetera, those type of concepts. The RSA method of public key cryptography. So this is a way to send a message in a secure but public way. So we have a message capital M. I'm going to raise that to the eth power, reduce it mod little m, and then I take that message, which is called the encoded message, and I raise it to the dth power to decode it. And the claim is that after encoding and decoding, we're back to the message we started with. So we need to show that MD equals M, in other words, that MD is congruent to M mod little m. Now why is that equivalent? Well, it's equivalent because both of these are reduced or least residues, which means they're smaller than m. So if they're both smaller than m, then being congruent mod m means they are equal numbers. So the decoded message is what? It's me to the d power. So this is really the original message raised to the dth power. That's very easy to show. And you want to show that's congruent to m mod m. Now m is a product of two distinct primes. So this is equivalent to showing that m to the de is congruent to m mod p and mod q. So just focus on one of these primes. It's going to be the same for the mod q argument. And ask yourselves, okay, how do I show that m to the dE is congruent to capital M mod P? Well, what does dE equal? Now we have to go back to the definition. This is the way D and E are defined. So we have that D times E is 1 plus LK for some k in the integers. So this is equivalent to saying that M to the 1 plus LK is congruent to M mod P. Aha! You can see the m to the first power over here, and our assumption is that capital M is relatively prime, so I can cancel that out. So I'm going to use the fact that MP equals 1 now, and then finally use the definition of capital L and Fermat's little theorem. So capital L is a multiple of P minus 1. Number 11. Show that if R1 and R2 are isomorphic rings with groups of units U1 and U2, that U1 and U2 are isomorphic groups. So we're given that there exists an isomorphism between R1 and R2. So let's let eta be ring isomorphism. So that means it's an onto mapping, and it's 1-to-1. And now we've got this subgroup of units U1, so let's let, say, eta hat be eta restricted to U1. So I'll write it like that. So that means I'm taking the domain of eta, which was originally R1, and restricting it to U1. Well, then clearly eta hat is a group homomorphism, since eta is both a ring, it's a ring homomorphism, so it's both multiplicative and additive. So what do we have to prove then? I have to show that the image of U1 is contained in U2. And that's going to follow from the multiplicative property of a homomorphism. The one-to-oneness is trivial, and so the only other thing we need to show is the onto-ness. Maps onto U2. But that's going to follow from the fact that eta has an inverse mapping, which is also a homomorphism, and it'll map units in R2 back to units in R1. Okay, and that'll establish that eta hat is an isomorphism between U1 and U2. Part B, show that the group of units in a Cartesian product is just the group of units in each of the rings put together like this. No. In part B, we want to show that if U1 through UK are the groups of units and R1 through RK, then the Cartesian product of these groups is the group of units in R1 cross RK. And that's just a matter of knowing what a unit means here. So what? So let's say UI is a unit in capital U sub I, so that there exists a V sub I in UI with UI, VI, equaling 1 and VI UI equaling 1. Okay, then if you look at the Cartesian product, or the ordered tuple U1, U2 through UK, and you multiply that by V1, V2 through VK, what's the definition? So the multiplication on a Cartesian product is just component-wise. So that's just U1, V1, U2, V2, UK, VK. Aha, well that's just 1, 1, 1, 1, 1, which is the identity element in this group, or it's the identity element in R1 through RK, and thus these are units in R1 times RK. Okay, so that's one direction, and then the converse is equally straightforward. I'll let you work that out.